You ever stop and think about the words you use every single day? I mean, really think about them. It turns out that some of the simplest words are packed with this incredible logical power. Words we use without a second thought are actually running on this secret engine, a kind of logic that governs how we talk about what's possible, what's necessary, and even what we believe. It all kind of boils down to a question that seems almost too simple. What is the real logical difference between saying something might be true and saying it must be true? I mean, we all feel it, we know they're different, but how do you pin that down? How do you define it with any kind of precision? So these words, might and must, logicians actually have a name for them: modal operators. And what we're going to do is pull back the curtain and see the elegant structure they're hiding. It's a structure that lets us reason not just about the world as it is, but as it could be. So, how do we crack this puzzle? Well, the key is this surprisingly simple but incredibly powerful idea. We're going to start thinking in possible worlds. Instead of just being stuck in our one reality, we're going to imagine a whole range of alternative realities. Just look at this comparison right here. On one side, the keys are on the table. That's a simple fact, right? We can check it. In our world, it's either true or false. But the moment you add that one little word, might, the whole meaning shifts. We're not just talking about this world anymore. We're suddenly talking about a whole space of possibilities. And this is the formal idea behind it all. It's called possible world semantics. Think of it as a tool, a framework that lets us evaluate sentences, not just here in our world, but across an entire landscape of alternatives. It gives us a really solid way to talk about what could be, what must be, and even what we think is. Okay, so how does this framework actually work in practice? Well, it all comes down to a really simple counting rule that splits possibility from necessity. It's all about asking, do we need to find something in just one world, or do we have to find it in all of them? And here it is. This is the absolute core distinction. For something to be possible, to say it might be raining, we just need to find at least one possible world where it's raining. Just one. That's enough. But for something to be necessary, to say it must be raining, that statement has to be true in every single relevant world we're looking at. No exceptions allowed. All right, let's make this super concrete. Imagine these 4 cards on the screen represent our set of relevant worlds for a moment. In a couple of them, it's raining, and in a couple of them, it's not. We're going to use our new rules and check some statements against this little universe. So, first question, is the statement, "it might be raining," true here? Well, what's our rule for might? We just need it to be true in at least one world. Let's check our set. Yep, look at that. It's true in world 1, and it's true in world 4. Since we found at least one, the statement is officially true. It is possible that it's raining. Okay, now for part 2. What about it must be raining? The rule for must is way stricter, remember? It has to be true in all worlds. So we check again. It's raining in world 1 and 4, yeah, but hold on. It's not raining in worlds 2 and 3. And because it's not true in every single one, the statement, "it must be raining," is false. And boom. That right there is the whole game. So we have this powerful one world versus all worlds mechanism. That's cool. But here is where things get really, really interesting. It turns out that this single framework can be used to describe completely different kinds of possibility and necessity. The secret sauce is all in how we define what counts as a relevant world. See, the meaning of must isn't fixed in stone. It changes depending on the context. Are we talking about what's possible given the evidence, or what's possible given the law? The framework stays the same, but the worlds we look at change. This flexibility gives us different flavors of modal logic. For instance, epistemic logic is all about knowledge. Here, the relevant worlds are all the ones that are compatible with what we know. Then you have deontic logic. That's about rules and obligations. So here, the relevant worlds are ones where all the rules are being followed. That's why you must pay your taxes. And then there's alethic logic, which is about pure logical truth. A bachelor must be unmarried in all possible worlds because that's just what the word means. It's the same core logic, just deployed to different sets of worlds. It's amazing. And of all those different flavors, one of the most fascinating has to be the logic of knowledge. Let's take a quick look at how this same exact framework can be used to create a formal model of what it means to actually know or believe something. Here's the key insight, and it's a big one. We can treat knowing as a form of necessity. So to say that someone, let's call her Sarah, knows some fact P is basically the same as saying that P is true not just in our world, but in all the possible worlds that don't contradict what Sarah already knows. It sounds a little complicated, but you can really break it down into 3 simple steps. Step 1, you take your person, Sarah. Step 2, you gather up all the possible worlds that are consistent with everything she currently holds to be true. And then, step 3, you check if your new fact is true in every single one of those worlds. If the answer is yes, then bingo, we can logically say Sarah knows it. It's become a necessary consequence of her knowledge. Now, I know what you might be thinking. This all seems like a pretty abstract, philosophical exercise, right? But this framework actually has profound practical importance for everything from understanding our daily conversations all the way to building intelligent AI systems. So what's the big takeaway here? The point is that modal logic isn't just some fun philosophical game, it's a seriously powerful set of tools. It lets us take fuzzy concepts like beliefs and define them with mathematical precision. That allows us to build proof systems that are absolutely crucial for AI reasoning. It even connects with other logical theories, like theories of time and context, to help us build a really full picture of what language means. So the next time you hear someone say might or must, just for a second, remember that elegant, secret engine of possible worlds running underneath. And it leaves us with a pretty fascinating question to chew on. If we can use logic to formally model something as personal and as fuzzy as belief, what other parts of the human mind can it help us map out and truly understand?